All right. Okay, so we are continuing on. We left off on Monday. We were talking about ordinary least squares regression in matrix notation, and where we left off was we had expressed the loss function, which is the sum of squared residuals, in terms of in matrix notation. So we said the loss function, after we kind of do all of the multiplication and we add them up, you know, is t, which is in our textbook, following our textbook notation, t represents the actual values. So, you know, you're probably accustomed to seeing the actual values represented as y's, as y, but for whatever reason, our textbook uses t. And so, you know, that's fine. And so if you represent them with matrix notation, we've got t transpose t minus, and then w is the vector of coefficients. In our case, w is a 2x1 vector with a intercept and a slope parameter. And it's, and we would have, after multiplying out the loss function, we get w transpose x transpose t plus w and then w transpose x w, okay? And what we want to do is we want to solve for the set of w's that will optimize our loss function. So we want to find the w's that will give us either the largest or the smallest. In our case, we want the smallest loss function. We want the smallest sum of squared residuals. And so we treat the actual values t as fixed, and we treat the input values x as fixed, and the only thing we can manipulate is w, the intercept and slope, the vector of w's, right? And so what we're going to do is we're going to take the derivative of the loss function with respect to w, set that equal to 0, and solve for w, right? And so when we do kind of derivatives, but in vector notation, we call them gradients. And so here is kind of a, this table is very useful in terms of taking gradients here. So one thing to note, and I didn't put the dimensions underneath each of these things, but this function outputs a scalar value, okay, a 1x1 value. And what we're doing is we're taking the output, the derivative or the gradient of this single scalar output with respect to a vector w. And when you do that, the gradient has the same dimensions as w. So in our case, w is a 2x1 vector, and therefore the gradient of w, or f of w, is going to be a 2x1 vector. And so here, if the function is w transpose x, okay, in this case, w transpose would be a 1x2, and x would be a 2x1, the gradient of w transpose x is going to be x, which will be 2x1. Here, x is 2x1 transpose, so x transpose is 1x2, and w is 2x1, and the gradient with respect to w also there is w, okay? If we've got w transpose w, this, you can think of this as almost like the equivalent of w squared, and what's the gradient, or what's the derivative of like x squared is 2x, okay? The gradient of w squared, or w transpose w, is 2w. And then here we have a matrix, okay, a matrix C. And in this case, if w is a 2x1, w transpose is 1x2, and this matrix C would then be a 2x2. So I've got a 1x2 multiplied by a 2x2 times a 2x1. The gradient of w transpose CW is going to be 2CW. So these are useful gradient relations to know, okay? And we're going to just apply that to our loss function. Okay, so we've got kind of all of these scalar values. So if I say, what's the gradient of t transpose t with respect to w? Well, there's no w in there, so it's just going to be 0, okay, right? Does it matter if c is positive semi-definite or symmetric or anything, like for quite, I think c has to be, I want to say C has to be positive semi-definite. That's a good catch there. Yeah, pretty sure C has to be positive semi-definite. So if we take the gradient of this with respect to W, it's going to be 0, okay? The gradient of this thing, W transpose X transpose T, okay? So X transpose T, will reduce down to a 2 by 1, right? So X is 2 by N and T is N by 1. So this, you can think of X transpose T as a 2 by 1. And so that's going to reduce down to X transpose T. And then W transpose, you can treat the X transpose X as that matrix C, right? So X transpose X, so if you treat that as C, then we've got W, basically a CW, and so that's going to result in 2 CW or 2 X transpose XW, okay? And if I do the dimensions, X is 2 by N, or X transpose is 2 by N, X is N by 2, and W is 2 by 1, okay? And so this reduces down to negative 2 over N X transpose T plus 2 over N X transpose XW. And so the gradient of this loss function, which is a 1 by 1 scalar with respect to W, ends up being a 2 by 1 matrix. Okay, so if W is a 2 by 1 vector or 2 by 1 matrix, then the nabla F, or the gradient of F, must also be 2 by 1. Okay, so all right, so far so good, I hope. Okay, and so what we are going to do is we have the gradient of the loss, okay, which is this. We are going to set it equal to 0, and we are going to solve for W, okay? So here I'm going to add 2n X transpose T to both sides, and then I'm going to kind of get rid of the 2n, okay? So this becomes X transpose T is equal to X transpose XW. And then to get rid of the X transpose X here, to isolate W all by itself, okay, there's no such thing as division in terms of matrices. You cannot divide a matrix. So this is a common mistake. So I think on one of the tests, I'm going to have you kind of just work through some of this stuff here. And if you try to divide by a matrix, you're going to lose points. You're not allowed to do that. What you are allowed to do is you are allowed to multiply by an inverse, okay? So what you can do is you can multiply by X transpose X inverse. So we're going to take this thing and we're going to multiply it by the inverse of X transpose X. And we multiply both sides by X transpose X inverse. And so when I do that, this thing and this thing will cancel out, will become the identity, X transpose X. The inverse times a matrix multiplied by its inverse becomes the identity matrix. And so here we're going to get just W over here. And over here we have X transpose X inverse X transpose T. And if you follow all of the, look at the dimensions, X transpose is 2 by N and X is N by 2. So this thing is a 2 by 2, and the inverse of a 2 by 2 is also a 2 by 2. And X transpose is 2 by N and T is N by 1. And so when all of these inner dimensions multiply, and this multiplies out to be a 2 by 1 matrix. And indeed, that's the solution W. So the W that optimizes the loss function is X transpose X inverse X transpose T. And maybe this is familiar to you already, maybe not. But this is a common result for least squares regression that represents the value of W that optimizes the loss function. Okay, so this is what we have. The OLS result is that the estimate of W that minimizes the loss function is equal to X transpose X inverse X transpose T. All right, so here is a quick example. X as the values 1, 2, 3, 4, and T are the values 1, 3, 2, 4. And if I plot them, this is what it looks like, okay? 1, 1, 2, 3, 3, 2, and 4, 4. Hang on a second. Let me pause my recording. Okay, Question, is there a reason why the book refers to beta as W instead of B? I thought B was pretty standard and our TA Jake has been using B. That's just the book's choice, okay? They use W to kind of represent weights rather than beta coefficients. So you are correct. In linear regression, it is very common to use B, beta, for the things. They're actually not British. They're Australian, I believe. I think they are Australian, but they have a little bit more in common with the Queen's English than us Yankee rebels. So so W is used for to kind of represent weights rather than betas. You know, I hope it's not too confusing. That's just what we got. So we got W's rather than the betas. So in linear regression, you know, beta shows up frequently, but I'd say in machine learning contexts, W is a little bit more common in terms of weights that appear. So that's what we have. Okay, so anyway, this is what I got: 1, 2, 3, 4 for X, and T is 1, 3, 2, 4. And when you plot it, it looks like this. To create our X matrix, the X matrix is n by 2, and so we have a column of 1s. So I'm going to bind the value 1 to all of the values X, and so this I'm going to create matrix X, and so matrix is a 4 by 2 matrix. And X transpose X, if I do X transpose X, I get a 2 by 2 matrix here. Okay. And that's just taking this and, you know, transposing it and multiplying it. So here's X transpose X. All right, the inverse of X transpose X, you can do it in R by calling solve. So solve on X transpose X gives us the inverse. And therefore, if I take this matrix and I multiply it by X transpose X, it would become the identity matrix, okay? And so what we have here is I'm going to multiply this by X transpose. So I got X transpose X inverse times X transpose. Okay, so X transpose X inverse times X transpose gives me a 2 by n matrix. And then I'm going to multiply that by the original matrix, not the original, the actual value matrix T, which is a 4 by 1 column matrix, okay? And so our W hats are X transpose X inverse, X transpose T, and that gives me W hat, which is 0.5 and 0.8, okay? And therefore this says the coefficient estimates are 0.5 for the intercept and 0.8 for the slope. Okay, so the best fitting slope and intercept and slope are 0.5 and 0.8, okay? And we can verify by calling LM. Okay, we got a question. It says, when you do T is C1324, does that give you a column vector or row vector? So it gives you a vector, okay? It is neither column nor row vector. However, when you take a vector and you throw it into a matrix operation, okay, R is going to automatically coerce this into a matrix. It's going to apply a dimension here. And by default, if you just turn this into a matrix, it's going to become a column matrix. It's going to become n by 1. All right. So this is 2 by 2, and this is T X transpose will be 2 by n, and then T, which is a length n vector, when it gets coerced into a matrix, becomes an n by 1 matrix. Okay. So when we call a linear model LM on our vectors T and X, okay, the R says the best fitting intercept and slope is also 0.5 and 0.8. So we get, so by doing the matrix operation, we get 0.5 and 0.8, and indeed that matches the results that we get of 0.5 and 0.8. Okay, so indeed, following the OLS, we get the same results. Okay, how are we feeling about all of this? Does this feel okay? Give me some feedback in the chat if something is not feeling good, or give me some thumbs up or thumbs down icons here. Okay. All right, let me give you the first viewing quiz answer for today. The first quiz answer is B as in bear. Bruins, I don't know. Baseball, B. B is our first quiz answer for today. B, I hope you guys heard that. All right. If you want to see what values you predict, right? So you can just take in a new value and, or your matrix of values, and you can multiply it by W hat, and these would be the predicted values. All right, so you just plug in the numbers you have, and so this we would just do X multiplied by our estimated W, X multiplied by our W matrix here, okay, W hat matrix. So I would do X times W hat, and this produces these four values. So X is 4 by 2, and W hat is 2 by 1, and so this produces a 4 by 1 column matrix of predicted values T hat here, okay? So, so here we go. These are the predicted values, X times W hat. All right, and if I plot the fitted line, this is what we have, okay? So these are the actual values, and this red line represents the fitted, best fitting OLS line, okay? All right, so let's go ahead and try this out for the Olympic data, okay? So this is, again, this is the running time of the winning time for the Olympic 100 meters race, okay? And so we're going to look at, is there a relationship between time and year, and this is what we have. And we can fit this using LM, and it says when you do this, the intercept is 36, and the slope is negative 0.013, which means every year that goes by, the winning time decreases by 0.013, okay? On a, this is what we have. Okay. If I do this in R, I can do this also. I take the column years, that's the X. We're using that to make predictions, and we'll bind that to a column of ones using C bind. Okay, so here's just kind of the head of our matrix, all right? And so I've got each year 1896. I guess that was the first Olympic Games where we recorded stuff here. And this is what we have, okay? 1900, 1904, I guess there was one in 1906. All right, and then, and we will estimate our W's by doing X transpose X inverse X transpose times the matrix, right? So one question, is it common to standardize the years, like make 1896 year 0? So it's not like we had a 36-second at 0 AD. So like, right, like when Caesar was emperor of Rome, we had the Olympics. I don't know, did they? I think, right? And but yeah, I don't know how they recorded time back then, but I don't think they had stopwatches, so I don't know if they would have recorded 36 seconds things. But yeah, you're right. We would not extrapolate. So right now we can just leave it as X. It is common to standardize, but it's not necessary. And as far as linear regression goes, it's not necessary to do that, but it can be done. Okay. So right now I'm not, and we're doing this. And when we do X transpose X inverse, X transpose times the original values T, or the actual values T, this is what we get. We get 36.309 with a slope of negative 0.0132. 0133, I should say. Okay, and if we look at what we have here, we get 36.309 and negative 0.01328. I guess if we round off, negative 0.01328. Indeed, we get the same values. The estimates match here. Okay, and then we can predict the values. We do x times our w hats, our w hat matrix of our slope and intercept, and these are the predictions for each of these years. Okay, and here we go. And this is what the line looks like when we fit the predicted values versus the actual values. So indeed, we get a straight line here. Okay, and here's the beauty. So right now you might be like, why are we bothering with matrix notation? Because in the beginning, when you first start with matrix notation, it can be frustrating. There's all of these dimensions that you have to keep track of, right? Like you didn't have to do any of this, but if I said like do it yourself, like you will probably find it to be frustrating in the beginning. Okay, but the thing about matrix notation is that you can often leave, as long as the dimensions line up, right? Right now we have a 2 by n. Okay, that n can accommodate different size things, and we can also change that 2 to some other thing. So we'll take a look at this. We can expand from matrix we can leave the matrix notation in as it is and expand it to allow for a nonlinear response from a linear model. Okay, so again, here's our Olympic data. And what if we want to fit a quadratic model, right? So I'm going to just add a column to x. I'm going to have a column of 1s, a column for x, and I'm going to take all of those x values and I'm going to square them. Okay, so I'm going to have a column of x of squared values here. Okay, and so here I go. Here's x. My big matrix x is going to be, I'm going to bind 1 and x squared. And so if you take 1900 and you square it, you get 3,610,000. Okay, and you square each of these values and you get these huge numbers. Okay, and when you have this linear model, okay, now we have 3 coefficients. Okay, we've got 3 weight values: w0, our intercept; w1 for our x term; and w2 for our x squared term. Okay, but in matrix notation, this is still going to be W transpose. If you have a vector or a matrix that combines all of these W terms, the weight terms, the predicted value is still W transpose X, or at least Xn for this thing. Okay, and that's exactly what we have for the linear model when we had one variable. Okay, so we have W transpose X. This is still W transpose X. Okay, and so the matrix of values of predicted values, we can take our column, our entire matrix X, multiply it by our column vector, or column matrix W. Okay, and indeed, this would be all of the predicted values is XW. So I do X times W, and this is what the model would predict for each of these things: W0 plus W1 X1 plus W2 times X squared. Okay, and that matches exactly what we want. So I've got XW, so this part remains the same. And the loss function is going to be exactly the same as before. 1 over n is going to be T minus XW transpose times T minus XW, right? Because the predicted values are given by the same matrix operation, which is XW. The loss function is going to be exactly the same as it was before, T minus XW transpose. So by using matrix notation, even though we've added additional terms to X and additional terms to our coefficients vector W, the formula, or the way we're calculating the loss, remains unchanged. Okay, and that's the beauty of working in matrix notation, is that I don't have to suddenly include an additional W term. It gets grouped up in here. Okay, and therefore when we find the estimates, we're going to still get the same thing. We're going to get X transpose X inverse X transpose T. Okay, If we did this the old-fashioned way without matrix notation using partial derivatives, our life gets much harder, okay? We would have to find the partial derivative with respect to W0, the partial derivative with respect to W1, and the partial derivative with respect to W2. And then I would have to solve all of those equations to find where kind of that system of equations equals 0, right? So I would have a whole bunch of these things to work with. Here in matrix notation, my solution for W hat remains exactly the same. It's X transpose X inverse X transpose T. I don't have to worry about finding additional partial derivatives and setting them equal to 0. Okay, and so this is why we prefer to work in matrix notation. This is why linear algebra is important and a prerequisite for the stats major, and all of this is because using matrix operations will simplify our life. And versus, you know, partial derivatives are great when there's only a few to calculate, but when you have a system of a whole bunch of these to work through, it's a major headache. So working in matrix notation makes our life a lot easier here. Okay, so my W hat remains being calculated the same way as before. Okay. However, what happens when I try this? If I say X transpose X inverse X transpose times T, I get this thing. It says error in solve default system is computationally singular. All right. So anytime you get an error, when it says error in this, you should say, okay, well, what's happening when I try to do this, right? Okay, so let's take a look. So when we do X transpose X, what happens? Okay, remember X was something like the year 1895 or 1896 and the year 1900. And when we square that, we're getting something like 3,610,000. And when we do X transpose X and we create a 3 by 3 matrix, look how big this number this is. This is 4 times 10 to the 14. That's like, I don't know what that is. 10 to the 9 is a billion, and 10 to the 12 is a trillion. So this is like 40 trillion, on the order of 40 trillion. It's a really big number, right? So this creates a problem. And then when you try to inverse, this matrix where we've got 40 trillion, okay, it breaks R, okay? Not breaks it, but basically, you know, finding the inverse of a matrix, you have to find the determinant. And if you remember from 102A, there's machine epsilon, right? On the computer is not actually dealing with real numbers, but it's dealing with binary representations of real numbers. And because it's a binary representation, there's a limit to how small of a number you can represent, okay? And we are pushing this limit when we are trying to take the inverse of this matrix where we've got 10 to the 14 here, taking that it causes problems, right? And it leads to a computational instability. The computer thinks we're trying to divide by 0 or something, and it says that the matrix inverse doesn't exist, and that's not true. It does. It's just that the computer's not able to handle it because of the way it represents numbers, right? So, so if you took 102A with me, you know, we belabored this floating point limit thing, but it's a real thing that you run into, okay? It's a real thing that you do run into, and these are things you have to take into consideration when you're dealing with a computer. We don't have real numbers represented in computers. We're dealing with an approximation, and sometimes we reach the limits of that approximation. Okay, so here's just a simple workaround, is rather than dealing with numbers that are on the order of, you know, 3 million and whatnot, I'm going to just take all of these numbers, the x squared numbers, and I'm just going to scale them down. I'm going to just multiply them by 0.0001, okay? So rather than getting 3,610,000, this is just 361. Okay, so this is all I'm doing, is I'm just taking that column and I'm going to scale them down. So we're not dealing with giant numbers, but something a little bit more manageable. Okay, and then when I do that, now I'm able to solve, right? Now I don't run into that matrix inverse quote unquote singularity thing. So I've just taken my scaled version and I can do X transpose X inverse, X transpose T. And we get values, and these are the coefficients that we have, 396, X and X squared, and these are the values that we're running with, okay? And if I were to fit LM, using LM on the values with our X matrix, we get the same values here. So if I ask R to use LM, so when R does LM, it's not actually doing this matrix operation stuff. This is mathematically, we can get W hats by doing this, X transpose X inverse, X transpose T. When R fits values, it actually does something different. I'm not 100% sure what it does, but it's not doing matrix inverses. And anyway, when you fit LM here, I do a 0 plus here because by default, R will try to fit an intercept term, and R will try to fit an intercept term, but here I already, in my X matrix, I already have a column representing the intercept. And so we don't need to fit a separate intercept term, so we put in 0 plus. This is the notation for saying don't fit an additional intercept, and the intercept is taken care of here. All right. So the question is, do we need to scale it back? So the answer is it depends. Okay. If you're just trying to get a prediction, no, you don't need to scale it back, right? You just take your values and you throw it in, and it just means when you make predictions in the future, it just has to come in this format. Okay. If you so you just have to kind of keep in mind that you applied a transformation to your input data in here. But in terms of making predictions, it doesn't matter because you can just get your predicted value. If you want interpretability, right? If you want interpretability and you want to say like there is this kind of relationship, then you'll need to kind of understand like what was the transformation that you applied, because there is a linear relationship between with the output value and this X scaled version squared. Okay, so so the interpretability, you would need to kind of scale it back or just understand what's happening. Okay, but a lot of times, you know, when you do some kind of prediction, right? Like if you do a log transformation. So if you've taken linear regression, like one of the things you might do is you might take your X values and you might do a log transformation. And as far as making the predictions go, it doesn't matter. As long as your new values undergo the same transformation, you can produce a new predicted value. If you want to interpret it and say, well, what's the relationship between the original X and the predicted value? Then you have to undergo and think like, okay, well, what we did to the original X is we transformed it, we applied this thing, and that's what's happening here. Okay, so as far as making predictions go, we don't have to scale anything back. We just have to take the transformed X, where we've scaled one of the columns, we multiply by the W hats, and these are the predicted values. Okay, and so when I plot that, this is what the predicted line looks like. Okay, so the predicted line, when I fit a quadratic or a squared term here, this is what we get. Okay, and this is how our model predicts, which seems to do a decent job. Meaning, and this also looks like it does a good job in that in the beginning the rate of the time improvements were great, and as time goes on, that the amount of improvement goes down and down. Okay, one problem with this though is that with a quadratic model, it means it goes the other way. It starts to curve back up, which means in the future people will be running slower and slower, which is obviously not going to be the case. But at least for the data that we have available, it does a decent job. Okay, there's a function in R called poly. Okay, and what this will do is it is useful in creating polynomial relationships for of higher order. Okay, and one issue that happens is that when you take do things like x squared and x cubed and x to the fourth, if you just take the raw numbers and you raise them to the powers, all of those numbers are going to become highly correlated, right? Like in all of those cases, as x gets bigger, the other numbers get bigger too. Okay, and we know high correlation creates problems in linear models. So what we can do is we can use poly, which is a function that creates uncorrelated polynomial versions of all of this stuff. You don't worry about the inner workings, but you can create x poly and it will do this. It doesn't do a coefficient term, and so we can fit models here. Okay, so here is the linear model for x poly, which is second order polynomial matrix. And again, we're using this mostly for just prediction. So these coefficients don't have inherent meaning because it's being applied to the scaled values here. Okay, so this coefficient has no intrinsic meaning. Okay, and neither do these coefficients. And this is what we have. Okay, and here's what our fitted values will look like. When you fit a model with LM, you can get the fitted values. Right, you store the results of LM into a model object. Okay, and we can do the model object $ fitted values here. Okay, hang on a second. Sorry about that. My kids are running around here. So, okay, so we can just take a look at the fitted values, and I can, and we can see how the fitted values are working here. All right. And what I'm going to do is I'm going to go ahead and fit polynomial models of order 3, third order polynomial, fourth order, fifth, and sixth order polynomials to our data. Okay. And this can be done very quickly by just calling LM and calling for the relationship between time, and then you just say poly x, third order, fourth order, fifth order, so on and so forth. Okay. And so I'm going to create a whole bunch of these different models without having to actually, take each of these x columns and raise them to a higher order here. Okay. And then what I can do is I can take each of these different models, and we can just plot the values and their fitted values, right? So, so I'm going to just take using each of those models, we're going to look at the fitted values, and we're going to just plot them using different colors here. And this is what it looks like, okay? And so this red line is the linear model, okay? And then all of these other ones, so we've got the linear model in red, and then as we go through the rainbow, we're going to have different order polynomials. So orange will be second order polynomial, green will be third, blue is fourth, purple is the fifth, and the gray one will be the sixth order polynomial, okay? And so we can see we've got the straight line in red, a quadratic one in orange. There's a little bit of curvature, third order polynomial, and all of this, okay? Can I again explain the benefit of using poly instead of squaring? Okay, well, first of all, poly is going to just be simpler in terms of notation and like the operations that you have to do instead of taking the column and then squaring them yourself and then having to scale them back if necessary. And then the second thing, and I didn't belabor this point, is that when you call poly, the different columns will be uncorrelated. So if you, because traditionally, if you take a column of x values and you square it, cube it, and raise it to the fourth and raise it to the fifth power, they're going to have high correlation. That as x increases, the x squared, x cubed, x to the fourth, x to the fifth will also increase. Okay, and what poly does is it transforms them into second, third, and fourth and fifth order polynomials, but it also kind of scales them a little bit differently in that they will end up being uncorrelated. So, because the issue is when you do x squared, if you start at 0 and go through 10, you're only going to get this part of the parabola. You're not going to get this. You're not going to get the whole you're not going to get the whole u part. Okay, you're going to just get the positive side, which has a positive correlation. And so what poly does is it looks at kind of the range from 0 to 10, and then it says, you know what? Let's fit the whole polynomial, the part that goes down and up across the range 0 to 10. Okay, and so there's still a quadratic relationship, but it has kind of shifted the values so that it's uncorrelated, right? So it goes both down and up, so that overall on the range from 0 to 10, it's uncorrelated, which is going to have better fitting properties rather than just having the linear part that goes from 0 to 10, which has this kind of relationship, and 0 to 10, which has, if you just square it, is just going to have the positive side, and that's going to be highly positively correlated. What it's doing is it's going to take that quadratic polynomial, the parabola, and it just it shifts it over so that there's still a quadratic relationship, okay, with the parabola, but it has centered it so that it is uncorrelated, if that makes sense, okay? And it does the same thing for a third order polynomial, and you have a cubic relationship and a fourth order polynomial. It will, it kind of shifts some of the coefficients around, so you still preserve the second order, third order, fourth order polynomial relationships, but it has made them uncorrelated. Okay. All right, so anyway, which of these models is best, right? So in a traditional linear regression class, you would learn things like AIC and BIC, or you'd look at the R² values or the adjusted R², and you would try to pick generally the rule of guidance is pick the simplest model that still has all significant things. And you'd look at something like this and you'd say, okay, well, this is how many stars I have. And you'd look at these different terms to try to decide which model is the best, okay? Or, you know, here's the sixth order polynomial, and you'd look at, you know, kind of the summary, and you'd say, okay, well, which of these terms is good? And, you know, we know that if you just use the R² value, that as you add more and more terms, R² is always going to go up. But, you know, are these terms, should I include those? You know, selecting which model is best is not an easy task, okay? And so I'm going to introduce cross-validation as a strategy for picking the best model, okay? Let me go ahead and give you your second quiz answer for today. The second quiz answer for today is D as in dog. D as in dog, and I hope you guys got that. D as in dog for the second quiz answer today. Okay. All right, so cross-validation is a way for us to help decide what model we should use, okay? So the traditional classical approach requires us to think about the variables, right? And we'd have to think like, does it make sense for race times to have a quadratic or cubic relationship to time like the year that the Olympics were held? What about a sixth order relationship? And what does that even mean to have a sixth order relationship with the year in which the Olympics were held, right? We have tools like AIC and BIC to help us select this, but it's difficult to do that and requires some skilled thinking, okay? So one thing, you know, the pro and the con of cross-validation is it removes the skillful thinking, or I guess on a con, it removes the skillful thinking. Pro, it removes arbitrary thinking, right? So when you say, yeah, let's go with the third order polynomial, or let's go with the fourth order polynomial, a little bit of that decision might be a little bit arbitrary, right? Cross-validation kind of removes that from the process, right? Which is both a pro and a con. And it just says, hey, let's just measure how well our model does at predicting values, right? Let's just take a look at measuring how well our model does at predicting values. So ideally, what you can do is you have like your training set, and you have additional data that you haven't seen yet, which we call the test set. And you say, well, here's the model that I fit. How well does it predict these new data points, okay? But that's often a luxury that we may or may not have, okay? And so what we're gonna do is, if we don't have the luxury of having actual new values that we didn't use as part of our training, what we're gonna do is we split the data that we have, the observed data that we have, into a training and a validation set, okay? And we're gonna take the training set and we fit the model on the training portion. So this is our total observed values. We're gonna like chop it somewhere. We're gonna say this is the training, this side's validation, okay? We fit the model on the training set. Fitting the model just means finding the right coefficients, finding the slope and the intercept. If there's more terms, you find all of those W or your beta terms, okay? That's the training part. And you say, all right, well, here's the model that I have based on the training set. Let's see how well this model does at predicting the values over here, right? We all know this, all of these values were generated by the kind of the process that we want to understand. And based on this, this is what we believe the process, and this is how we can predict values. Let's see how well it does, right? We know these are real values and we can test or validate how well our model performs, right? And we're going to use some way to measure how well our predictions work. Usually we often use MSE or something similar, which is like, I predicted 7, the actual value was 7.2. That's a good prediction. I predicted 7, the actual value was 15. That's a bad prediction. We're going to take the error, we're going to square it, and we take the mean. So the mean squared error is often kind of how we measure how well our model predicts, okay? And we do this for all of the different kinds of models. We're going to say, all right, let's fit the linear model and see how well it performs. Let's fit the quadratic model, see how well it performs. Let's fit the third order polynomial or cubic model and see how well it performs, right? Okay, does cross-validation also contribute to reducing overfitting? Yes, so cross-validation is one way for us to avoid overfitting, and I'll show you an example of this later today, okay? So I got a whole bunch of slides to kind of rip through here, okay? And so I'm going to start off with what's called leave one out cross-validation. This is a very simple version, okay? And in leave one out cross-validation, basically you're going to take all the data that you have, and pretty much all but one point will serve as the training data, okay? So you're going to just remove one observation. You leave one of them out. You train the model on the one observation that's left out, and the one observation that it's left out serves as the validation set, okay? And every data point in your data set gets a turn at being the validation data point, okay? And then, so you're gonna have, if you have n data points, you're gonna fit n different models, okay? You're gonna have n different training validation sets, and you're gonna fit the model n different times, and you're gonna measure how well it predicted the last one, okay? So I'm gonna just show you, we'll do it for our toy data set, okay? Our data set is 1, 2, 3, 4, 1, 3, 2, 4, okay? And I'm gonna say we're gonna use observations 1, 2, 3 as my training set. Okay, and then we're gonna measure kind of the, we're gonna measure the error on the validation set, okay? So in the code, I take, I subset X into training X, and I subset the actual values T to training T, and then everything but I remove the index will be my validation point, my validation T, okay? And then I fit the a linear model on between T and X using the training data, okay? I fit a model using the training data, okay, where I've combined train X and train T into a data frame. And then we're gonna take a look, okay? So this is what the linear model would look like if we fit it to all 4 data points, okay? But what we're gonna do is we remove, okay, we remove this point, right? This point is gonna go away. So if this point goes away, then I'm left with these other 3 points. I'm like pointing to my screen, but you guys can't see my finger. Okay, so we're looking at the other 3 data points, and we're going to say, what is the best fitting linear model for the other 3 data points? So if we only have these 3 data points, this is the best fitting linear model. Okay, all right, and now we say, how well does this model that was fit on these 3 data points predict the data point that we left out, right? We left one out, and if we fit a model on these 3 data points, this is the best fitting model that we have for these 3 data points. How well does it predict the one we leave out? Okay, and so we measure the distance, and coincidentally in this data set, it predicted 3, the actual value is 4, and so the squared error is going to be 1 squared, which is 1. Okay, so what we're going to do is we're going to measure the total deviation, and we're going to go through the deviation, and we're going to measure that. We're going to square that deviation, and we're going to keep track of the total squared deviation. Okay, so far, right, my total squared error, so it starts off as 0, and I'm going to just add my squared error of 1, okay, to it. Okay, so for each of these things, what I'm doing is we're going to make the prediction, okay, on the validation set X, and then we take the difference between the predicted value, t hat, and the actual validation point, okay? We're gonna take that difference and we square it. That's our squared error, and we're gonna tack on the squared error to the total squared error. So right now this is 0. We add 1, and so my total squared error so far is 1, okay? Then I do this. Each data point gets a turn at being the validation set. Okay, so what I'm going to do is we're going to pull this one out. This is the one we leave out. Okay, so if I hide this data point and I only have the other 3 data points, if I only have these other 3 data points, what's the best fitting line? What's the line that's going to best fit the remaining 3 data points? Okay, this is the line that best fits the remaining 3 data points. Okay, and we say, okay, well, how well did it predict the data point we left out? So we put the data point we left out back in, and we say, okay, well, how well does this line predict this data point we left out? We measure that distance, okay, and the squared error here is 1.6531. All right, is this process okay? The idea of leaving out a data point, we fit this linear model or whatever model we're using, we fit the linear model to the remaining data points, and we say, okay, now that we have this, how well did it predict the data point that we left out? Okay, again, if you're not feeling okay, give me some feedback here, throw in a question here, okay? And we do this for every single data point, okay? So here again, here's all 4 data points. We're gonna leave this one out this time. Okay, I hide that. We say, what's the best fitting line? This is the best fitting line for the remaining 3 data points. How well did it predict the one we left out? The squared error here is 1.6531, okay? And then, again, here's all 4 data points. We're gonna leave this one out. How well did, this is the line that fits these 3 data points. How well did it predict the one we left out? And that squared error is 1. And we add up all of the values, okay? We had 1, 1.6, 1.6, and 1. And when we add all of those up, we get 5.306. So that's the total squared error. And then if I take the mean of those, we had 4 of them, and we divide them, we get a mean squared error of 1.3265. All right, cross-validation here. All right, so here we have a question. If we're using a large data set, would we use a portion instead of a single point? So for leave one out cross-validation, you're doing one at a time, okay? But yes, you're absolutely right. For a large data set, like if you have 100,000 data points, you don't really want to do this 100,000 times, right? You'd have to do 1 point at a time. And so that brings us to k-fold cross-validation, which I will talk about in a few slides here, okay? So you've got the right idea. We're just jumping the gun a little bit, okay? So we've done it for the small data set. We left one out at a time. We calculated, you know, how much the squared error is when we leave it out. And we got a mean squared error of 1.326, okay? All right, so this was how I did it manually. R has built-in functions just that pretty much can do all of these things. So here inside library boot, you can call cross-validation.glm. So GLM is basically generalized linear models, which can also fit regular old linear models. So I do the linear model, and then we're going to do cross-validation on the GLM, and the cross-validation mean squared error is stored in delta 1, and it gives us this 1.326531, which is exactly what we found when we did it ourselves, added them up and divided by 4. Okay. Okay, when you use cross-validation to evaluate a model, you're going to get one cross-validation score for that model. In this case, for the linear model, the cross-validation score is 1.32, 1.326, okay? And, you know, what we're doing is we had 4 data points, so we fit the linear model 4 times, and it produced kind of 4 different cross-validation errors, and then we took the average of all of those things. The total cross-validation score for the linear model is the mean of those 4 values, okay? And so this all by itself, probably not super useful. But where it's useful is when we take the leave one out cross-validation score for the linear model, and we compare it to a leave one out cross-validation score for a quadratic model or a cubic model or whatever it might be, okay? This is just kind of a summary of the pictures of where that number 1.3265 comes from. So this is, you know, we trained on points 2, 3, 4. The actual value here is 1, and so the squared error here is 1, and 1.6, 1.65, 1. And when you add up all of these things, you get this, and you divide by 4, and you get 1.326. So again, this is where the model is, okay? Okay, so question. So in linear models, cross-validation is only used for model selection, but not model training? Yeah, cross-validation is purely a model selection tool. You are using it to evaluate one possible model versus another possible model. Like, do we want to create a model that uses only this variable, or do we want to create a model that uses multiple variables? Cross-validation is used to just help you decide which model is the one you should use. It's not something you use just all by itself, okay? There's generally competing models, and you use cross-validation to compare one to another, okay? So after we fit the model n times, we get the mean squared error as our cross-validation score of 1.326. And we can try a different model, maybe a log-log model. We're going to fit that log-log model n times, or 4 times in our case. And we get a validation error each time. We average all of those, and we get a cross-validation score there. And then we compare cross-validation for one model to another model to help us decide which model is the best, okay? If there's only one model and you're determined on using that one model, there's no sense in doing cross-validation, okay? I mean, maybe you can use cross-validation to get a sense of how well it might perform in the future, but generally cross-validation is very much a model selection tool. Okay. All right. So, you know, earlier we had the question of, if we had a very large data set, should we use multiple points instead of 1? Okay. And that is k-fold cross-validation, right? So leave one out cross-validation has major drawbacks, right? You have to fit n models, which is computationally expensive if you have a very big data set, okay? And then also another problem is that because all of the models are fit on all but one data point, the resulting models end up looking very, very, very similar to each other. And the resulting kind of coefficient estimates end up being highly correlated, and you can still overfit the training data, okay? So for a large data set, the alternative is to use k-fold cross-validation. And what that's gonna do is it's gonna take your data set and it's gonna break them up into k approximately equal sized blocks, okay? If it can be divided by k evenly, then you're gonna have k equal blocks, but it might not be, like if you try to divide by 17 or something, maybe it won't work, okay? One of those blocks serves as the validation set, while the remaining blocks combine to be the training data, okay? So if we do 4-fold cross-validation, the remaining 3 chunks will be trained, and you validate on this one. Iteration 2, you know, the second chunk serves as the validation. Here, iteration 3, the third chunk serves as the validation. And here in iteration 4, the fourth chunk serves as the validation. You know what? I've been talking for a long time. Why don't we take a 5-minute break here, and we'll come back. Or we didn't take a break already, did we? I'm like losing
No, we
track. Okay. Let's go ahead and take a 5-minute break here. Oh, did I give you, how many quiz answers have I given you?
2.
2. I've given you 2 quiz answers. Okay. All right. Well, let's take a 5-minute break, and then we'll come back and we'll finish out the lecture, and I'll give you the last quiz answer. Okay. All right. Let me pause the recording here. All right. So the question is, for k-fold cross-validation with a categorical variable. Oh man. Okay. So all of this validation stuff is mainly for numeric outputs. Okay, but let's say for a categorical variable that has a lot of levels, is there a chance that it will predict badly because one of the subsets doesn't include a factor level? That could happen. That could happen, yeah. Like looking at class performance in 100 different classes and each class has its own effect. Yeah, that's not an ideal scenario, right? Ideally, right, if you have like 100 different classes, you need a lot more than 100 data points, right? You need multiple observations in each data point of each possible output class. Otherwise, there's no way of being able to predict it, right? Like if you only have one observation for a certain class output, then it's going to be very skewed, right? It's going to be that one observation is the only representation you have of that particular class, right? So, you know, this is an example that I'm thinking in mind. This is probably not a great example, but you know, prior to going to college, if you lived in a small town, you might have only encountered one person that came from a particular country, and that person is the one representative you have for that entire country or something, right? And of course, we shouldn't try to judge like an entire nation based on one person, but if that's like the only person you've encountered, you might think like, huh, you don't know if it's that one, if it's like, and if that person does something unusual that you've never seen before, you'd be like, is that just this one person who's a little bit strange, or is everybody from that country a little bit like that? You know, and so if you have a data set, right, and this is not a great example, but if you have a data set where you have 100 different classes and you only have like 1 or 2 representatives for that particular class, yeah, you're going to be in trouble. So generally you want at least k representatives of each possible output class. And then if you're going to do cross-validation, you know, you can actually specify that you want it split up so that each of the different, it's not like purely randomly split up, but it's kind of split up in a stratified setting so that each of the k folds has like all of the classes represented and stuff like that. And that's possible. But yeah, it's quite difficult. So all of these things, you know, mean squared errors can only be applied when you have a numeric output, and you know, we can do things, but so far we haven't talked about classification yet. Okay, is that all right? I hope that helps answer your question. Okay, so we left off with k-fold cross-validation, and so we're dividing up our data into k different folds, and we're using each of the folds gets to serve as the validation set. Okay, so here let me just show you what happens. We've got the Olympic data set. We've got 28 observations. Okay, so if I look at the dimensions on the Olympic data set, I've got 28 observations in 2 columns, right? And we're using year to predict time, and I've got 28 of these things. So I can do four-fold cross-validation. This is the full data set. And what I can do is I can do four-fold cross-validation. So I'm going to divide the data into 4 random blocks, okay? And so we're going to have 7 observations in each of these blocks. And each fold is going to serve as the validation split, okay? And we are going to fit a whole bunch of different models on each validation set, okay? We're going to fit the linear model, quadratic model, cubic model, a 4th order, 5th order, 8th order, and just for funsies, we're going to try fitting a 17th order polynomial model, okay? So each training set will have 21 data points, right? So we've got 28 data points. Each one has, each fold has 7, and the remaining 3 serves as the training set. So we're going to train our model on 21 data points. Once we fit a model on those 21 data points, we're going to use that to predict the remaining 7, okay? But the 7 data points are random, so it's not like the first 7 and the middle 7 and the next 7. It's just 7 randomly picked at a time, but all 4 blocks will create the full set of 28, okay? And what we're going to do is we're going to calculate the total squared error for each of the validation sets, and then we're going to find the cross-validation score by averaging the squared error for each of these different models. The linear model, quadratic, we're going to do that, and we can compare the cross-validation scores to help us select which model is the best, okay? Okay, so I'm doing this manually. There's ways to kind of do this automatically in R, but just for manual, I'm going to shuffle up the values 1 through 28, okay? And then we're going to take 7 of them and put them in set A. We're going to take the next 7 and put them in set B, the next 7 in set C, and the last 7 and put them in set D, okay? And so I've got 4 sets, okay, or 4 folds for my 4-fold cross-validation. And then we're going to store our results of the total squared error in cross-validation linear, quadratic, order 3, 4th order, 5th order, 8th order, and 17th order. Okay. All right, and so here is just the beginning part of the code for cross-validation, okay? So here we're going to take one of the sets, okay, either set A, B, C, or D. So the first time it's going to be set A. Okay, and we're going to store them in validation index, okay? And therefore my training data, okay, I'm going to take train X and I'm going to take all the years and remove the validation indices. And then my training T's will be the time, and I'm going to remove the validation indices, okay? And then for the validation X, I'm going to subset the years to just the validation index and subset the times to just the validation index, okay? And then I create my data frames. My training data frame will be the training X and the training T, and my validation data frame will be the validation X and the validation T, okay? And then N is going to be 7, but that's the length of how many values are in my validation index, okay? So N is 7. All right, and then so for what I'm going to do is on when I'm having validation set 1, I'm going to fit model 1, which is going to be the linear model. We're going to predict T based on X using the training data only. Okay. Once I have the linear model that I've created using the training data, I'm going to create my predicted values. Okay. Predicted values will be, I use predict on model 1, where the new values that it needs to make predictions will be new data is equal to valid, right? So I have my validation data frame. I plug that in here to create predictions, and that's going to be my T hats, okay? And then so my sum of my squared errors, okay? I guess the mean squared error here is going to be the difference between the actual data, validation set $T, that's the actual values, minus the T hats. Okay, I'm going to square that value. I sum that up and divide by 7, divide by N. So that's going to be my sum of squared errors there. This would actually be the mean squared errors here, okay? I do the same thing this time for a quadratic fit, okay? I'm gonna fit t based on polynomial of degree 2 using the training data, okay? So this forms model 2. And now that I fit the polynomial, I'm gonna take this and I'm going to make a prediction using new data, using the new data where I've got the validation set, okay? And so this is t hat 2. I take the difference between the actual values and my predicted values, t hat 2. I square that, sum them up, and divide by n, okay? And that's gonna form the value I put in for cross-validation for the quadratic fit, okay? And this is basically the same text that I've had before, but I do the same thing for polynomial order 3. I do poly x3, polynomial order 4, poly x4, polynomial order 5, poly x5, polynomial order 8, poly x8, and then this is all done up with poly x17. Could you have done a second loop with poly x1? I could have, but then I would have had to find a creative way to store it. So yes, absolutely. You know, I'm like copying and pasting code, which is kind of the, I should have done something like done a little bit better. But here, just to kind of keep my life a little bit, I don't know, easier or just easier to kind of mentally track, I have different, I've created different vectors to store the mean squared errors here. As CV order 3, order 4. I could have, you're right, I could have created an inner loop or a function to do this and store the results in some kind of matrix or something. That's also possible, but I hope this is okay. All right, there's a balance that I have to run in creating these slides, is just keeping the code lexically simple enough to kind of just follow along. All right, so just to be clear, when you see t, you should think of the response variable like y. Yes, I'm following the textbook's notation where the response variable is t, okay? But yes, if it's easier for you to understand in your head that we are talking about y, the output variable y, then yes, yeah. So t is y and w is beta, yeah. So for linear regression, you're probably accustomed to y's and betas. But for machine learning models, we often encounter T's and W's or Y's and W's. So our textbook chose to use T, the author chose to use T. And so that's what we have, okay? So here's just one example, okay? Where I have, we're gonna just look at one of the validation sets. What's the etymology of T? Oh, you guys are asking, impossible questions. I don't know. I don't know why we use Y and W. Yeah, it's not time. It's not necessarily time. It's just T. I don't know. Truth? I don't know. I have no idea. I don't know what T is supposed to represent. That's just what the authors chose to use. Okay. All right. So we're going to look at validation set C, which I've highlighted in red. Okay. So these are the 7 data points that form our validation set. And what we're going to do is we are going to remove those 7. Okay, we're going to remove these 7 data points, and we're going to fit a linear model to the remaining blue data points. I mean, not remaining 21 data points. Okay. Yes, T as in target. That is correct, actually. Thank you. T is like target. That is the right answer. Thank you. I didn't. That is, you are right. Okay. So we remove the red data points, and we fit a model to the remaining 21 data points. Okay. And then we throw the red data points back. Okay, looking at just this model, and we say how much error is there between the validation set, the red data points, and the model we've predicted. Okay, so here's the full data set. We remove the red, the validation set, and we fit a model to the remaining points. And then we bring back the red data points and we say how much error is there, right? And so some of the points it predicted very well, right? These data points are exactly, or not exactly, but very close to the predicted line. Others, there's some error, okay? There's some error here. And so the mean squared error for this validation set is 0.03, okay? If we look at, so again, we remove, here's the original data set. If I remove the, those red data points and we fit a quadratic model on the remaining 21 data points, this is what we have, okay? And then again, we bring back the red data points and we say, how much error is there? Okay. And so for the quadratic model, this is the amount of error. So we look at each thing and we say, okay, well, how much error is there? And some of these are close, some of these are a little bit farther, and we take the average, the mean squared error for this particular validation set, and we have 0.025. So that's the quadratic model. Okay. Again, we look at the, after we remove the 7 validation points, we'll fit a cubic model. So this is the cubic model that's fit to the remaining 21 data points. And we say, how much error is there between the cubic model and the remaining 7 data points, okay, the validation set. And in this case, there's very little error. Some of these dots came very, very, very close, okay? And so the mean squared error for this validation set is 0.013. All right, is this okay? Are all of these pictures okay as far as what's happening? We're fitting the model. The fitted model, the prediction line is fit on the 21 data points, and then we measure its performance on the 7 data points that were left out, okay? So we've partitioned the full set of 28 into basically 21 and 7, and we fit a model on the 21, we say how many, what's the line that best fits those 21 data points, and we say how well does it predict the remaining ones, okay? Here it is for the 4th order polynomial, okay? We get mean squared error of 0.019. Here it is for the 8th order polynomial, okay? And now we start to see some of the problems of using a high order polynomial, right? With an 8th order polynomial, we get some things starting to curve up here, okay? And we can see, okay, well, you know, now we're starting to get some deviations here, okay? And then here it is for the 17th order polynomial that we did, which was kind of silly. And you can see when we fit the 17th order polynomial on the set of 21, it actually does a pretty good job of fitting the visible data, right? Like it fits these ones perfectly, okay? And there's very little error here, okay? But when we take this same line and we say, well, how well did it predict the remaining 7 data points? It did a terrible job, especially this one, because it's 17th order, this like shoots off to a crazy value. And so there's a huge, huge, huge residual between this line and this line. It went off the page, and the mean squared error here is 1,640, okay? It did a really terrible job of predicting this line. So it's very bad, right? And we got huge difference because it was trying to fit the visible, the observed data, right? So this is a case where we are overfitting. We are overfitting the available data to us, and when we try to validate it on other data points, it does a terrible job here. Okay, all right, we have a question. So if we had to do this for leave one out cross-validation, the length of the CV line full of vectors would be the length of the original data set. Yes, you would have however many train validation splits you have, it will be the length of your cross-validation vector. Yeah, so if you have 28 data points, it would be a length 28, okay? But yeah, so here we've got four things, and that's what we have. All right, is there such a thing as piecewise fitting, like 17th order for the first bit, then remove the crazy shooting off at the end? So like we go 17th order up to here. So there is a way, like you can specify models that, you know, say we're gonna fit, you know, quadratic here and linear here and something here. But the idea here is we're trying to fit a model that can be kind of automated, all right? In that, you know, if you keep having to like manually intervene to try to clean things up, how well is this going to work in production, right? In a production setting, in machine learning, you don't want to have the human constantly intervene and things like that, right? So that's part of the idea is, you know, you can specify these complicated models that say, well, we're going to choose this and this and this and this, but you kind of want to have a little bit of an automated procedure. And so you might have to say, well, fit a quadratic model if it fits like this, and a linear model if it fits like this, and things like that. And you need a kind of a set of rules rather than just you as the human kind of arbitrarily saying, because it looks good to me, I'm going to do this, and it looks good to me over here, I'm going to do this. You need to kind of have some kind of rule set so that the computer can fit the model on its own without humans intervening here. Okay, so we can see the 17th order polynomial maybe fits the training data well, but does a very poor job on the validation set, okay? And so if I keep track of all of these things, we've been looking at validation set C, but if we look at all 4 of the validation set A, B, C, and D, we can see how the linear model, quadratic model, third order polynomial, and things like that fit, okay? And for validation set C, we can see for the 17th order polynomial did quite poorly. It actually does, 17th order polynomial does poorly for all of the different validation sets, okay? And what we would do here is we would look at the overall cross-validation score, and we would go off of this, okay? And here, based on the average, so if we take the average of each of these cross-validation scores, okay, if I average these numbers, we're going to get 0.0674. If I take the average of this, I get this, and we are not, what do you call it? We would pick this number here, okay? And so based on this, the 8th order polynomial happens to have the lowest average cross-validation standard error, okay? The third order polynomial has the second lowest as at 0.0571, okay? And we would probably pause to think about which model we would choose, and I would probably argue to use the third order polynomial, okay? Sometimes your cross-validation results are the result of just how the, you know, when we split them up, the 28 data points into 4 sets of 7, okay, into 4 sets of 7, just by random chance, as far as the different sets of 7 go, there could have been different results here, okay? And so, you know, the rule of thumb is you generally go with the lowest cross-validation score, okay? And I'm so sorry, let me hang on a second here. Okay, so we would look at the cross-validation score here. And so, so yeah, we would look at this and we might be tempted to go with the 8th order polynomial. I would recommend trying to run the cross-validation set, cross-validation again, the k-fold cross-validation again with a different splitting of the 28 data points into different k-folds and just kind of seeing how that performs, okay? And so if I tried a different random seed here, so I did set seed 7, so back here when I split the, all the way back here, when I split the data into 4 different cross-validation sets, I use set seed 5. Now, when I try a different seed, okay, with a different starting seed, and I do this, now the 8th order polynomial does not perform well. It actually performs quite poorly compared to the others. And we can see the third order polynomial performs the best, okay? And so depending on how your k-fold cross-validation was split, okay, the random seed in terms of dealing out the 28 data points into 4 different sets, you might get slightly different performance. So that's something to keep in mind, okay? Cross-validation is useful, but doing just one run of it might not give you the best, might not give you the quote unquote correct answer here, okay? Leave one out, cross-validation, there's going to be no variance because every time you run it, you're going to get the same. Each data point will serve exactly as a validation set every single time. But when you do k-fold cross-validation, there's a little bit of randomness that comes into play here. Okay, here it is with just another random seed, set seed 10, and what are the results? Okay, here the third order polynomial performs best. Okay, so is it common practice to loop over tens of several different seeds? I guess it depends how much computational excess you have, right? So a lot of times, if you're dealing with a fairly large data set, we don't have the luxury of being able to do cross-validation like several different times. We often don't have that luxury. So a lot of times, I would say probably most common is you do it once and you hope for the best. But that might not be, it might not be right, okay? And that's often the case with statistics, right? When you go out and you do an experiment and you spent, you know, $100,000 testing out a new drug, right? Like right now, millions, possibly billions of dollars are being spent to test vaccines and possible treatments for COVID-19. And I don't know how many people they're testing on, but if you have a small sample size, right? We're hoping this is representative of the population, but we never know, right? And we don't have the luxury of running on the population before releasing it to the public. And so you just kind of have to, you test it on your group and you hope for the best. And often that's the case when you even do cross-validation, is you often don't have the luxury of doing tens of different seeds. And so you have to hope for the best. But I'm just illustrating this to you to kind of give you a warning that just because you ran cross-validation once, it's not 100% the right answer. And it's not always going to be consistent. Okay, so these are things to be aware of. Okay, do we always use one predictor models in cross-validation? What do you mean by one predictor models in cross-validation? How do we determine the size of our blocks? Yeah, k is an arbitrary number. I think we often like to do 5-fold and 10-fold cross-validation just because we have 5 fingers and 10 fingers. But I would say those are probably common choices, is 5-fold and 10-fold cross-validation. But you know, there's no rule that says it must be. Yeah, one predictor models, I'm not sure. You can use different kinds of models. You can use multivariate models, all sorts of different models. Cross-validation is to help you decide whether one particular model that uses these predictors or other predictors is a better or is a good, how it performs compared to another model, okay? And so anyway, to sum it up, it's possible to get different cross-validation results where a suboptimal happens to perform best, okay? And if you're able to afford the computational expense, you know, it's recommended to run cross-validation more than once, but sometimes you aren't able to afford the computational expense, especially if you have a giant data set. And, you know, other problems is that, you know, that data set in of itself may not be representative of the general population, right? I think this is a common thing that's happening with AI and machine learning things, is that you know, for like facial recognition and face processing and stuff like that. The training data sets that that exist and are currently being used, the training data sets, a lot of them are mostly white people in terms of like face data sets that we have. And so a lot of these models end up being biased towards predicting white European looking faces and things like that. And so there's, so even having a giant data set might not solve your problem if your data in of itself is not fully representative. So this is things you have to be aware of and things to keep in mind. Yeah, that's exactly right. That's the example I'm thinking of. Is that I think on Twitter there was a thing where they gave it a pixelated version of a face, and then the machine learning model or the neural network tried to predict what the original face looked like, and they gave it a pixelated version of Obama's face, and it created a white man. And you know that there's a lot of debate as to, you know, what's the reasons behind it. Okay, is it the models itself? Is it the data? There's all sorts of questions, but you know it's an issue that that the machine learning community has to think about and be very aware of. Okay. Okay, you can do cross-validation, k-fold cross-validation using library boot. So you got cv.glm. Okay. And so I'm going to just run cv.glm, and there's some variation between the runs because the random blocks that get created are different from run to run. But when you do leave one out cross-validation, there's going to be no variation between runs because all the points serve as the validation set one at a time. So, so let me just show you here. Okay, so here I do the linear polynomial order 1. So this is a linear model. And if I do a 4-fold cross-validation, I get values like 0.0643, 0.0659, 0.0576. Okay, there's slight variation in the CV scores that we get. Okay, and that's again because when we're splitting up the data into k-folds, there's variation in each data set. Okay. What if for a certain k-fold model, it does not divide the sample evenly? You know, so basically it just calculates the thing and it divides by how many data points there are. So it's going to get the mean squared error, so which takes into account how many data points you have. In general, you get fairly evenly sized blocks, but yeah, it's not going to be perfectly even. Okay. Here it is for a second order polynomial, and again, there's variation between the results. Okay. Third order polynomial with 4-fold cross-validation, again, variation between the results. Okay. However, if I don't include the argument k equals 4, then it performs leave one out cross-validation, and the result's going to be exactly the same because the validation sets, there's going to be 28 validation sets, and all 28 validation sets is one data point at a time. And so you're going to get the exact same result each time. So this is leave one out cross-validation. And if you're looking for kind of a consistent answer, then you can do this. But again, it requires a lot of, it's computationally expensive because if you have a large n, you have to fit the model's n times. All right, so in summary, okay, cross-validation is a method that we can use to see how a particular model will generalize to new data. The idea is we've trained a model on some data, and then we're using it to make a prediction on data that was not used in the training process, okay? And so, oops, what happened here? The goal of cross-validation is, yeah, to test the model's ability to predict new data that was not used in estimating it, not used in fitting the coefficients. And it can flag problems like overfitting. Like if the cross-validation error comes back huge, it's an indicator that you've overfit, okay? Multiple rounds of cross-validation are performed using different partitions, and validation results are combined or averaged over the rounds to give an estimate of the model's predicted performance, okay? So there's leave one out and k-fold cross-validation. And for your homework, okay, as far as your homework goes, you will be doing a little bit of cross-validation yourself, and so I've kind of walked you through a lot of it here, okay? And so, you know, there's lots of instructions in here, and I apologize for being so verbose, but I'm hoping it will be a good learning experience for you as you work through it. Okay, are there, do you guys have any questions before we go? Oh, let me give you, did I give you the last quiz answer? I don't think so, right? Okay, last quiz answer today is A as in apple. A as in apple is the last quiz answer. Question 3, A as in apple. Make sure you take your viewing quizzes. They're worth a bit of your grades, so there. All right, if that's it, we will end here. How important will style be in homework grading? I am not a super stickler for style, and I'm hoping you learned decent style. But you know, obviously, make sure you're not writing super crazy long lines that it doesn't fit in the output. Make sure all of the output that's requested appears in the file, in the PDF file that's being graded. Okay, and I did say A. I did say A for the last question. Third question today is A. Okay. Any other questions?